This is May 2015's paper of the practical examination, Booklet B. So the first part of your paper is always going to be a titration calculation. So obviously in the actual practical you did your calculation, you recorded your values, but you didn't do any calculations. So what they will do, they will give you a set of results and they will ask you to do some calculations, some interpretations from that. So as you can see, last year the titration question was on iron, the iron permanganate titration, this type. And the first question is writing the ionic equation for the reaction of these tablets. So the question says these tablets. These tablets are made up of iron sulfate and potassium permanganate solution. So I would advise that this is an equation that you have just learnt off, the reaction of permanganate and iron ions. But we can also build it from scratch if you were to forget, and we'll do this above here. So firstly we have manganate ions being reduced to manganese ions 2+. So how do we form our half equation from this? Well, if you remember, our stepwise process is to firstly balance our oxygens with water. So we have 4 oxygens on the left hand side, and so that means we need 4 waters on the right hand side. And then our next step is to balance hydrogens with protons. So we've got 4 times 2 hydrogens on the right hand side. So we need to have 8 hydrogen plus ions on the left. And finally then we need to balance the charge with electrons. So think we've got a minus here plus 8 positives. So that's an overall charge of +7 on the left. And then we have our just 2 plus here. So our overall charge on the right is +2. And so we balance our charge with electrons, and so on the left hand side, and I have no room after the equation, so I'll just write it at the start, we need 5 electrons. We need 5 electrons to balance out that charge. So that's our half equation for manganese. And then what's happening to our iron? Well, our iron 2+ is being oxidized up to iron 3+. Okay, and here we don't have any oxygens or hydrogens, so we just need to balance our charge with electrons. And so this time there's going to be an electron on the left hand side. Okay, we can form our ionic equation from here. But we need to have the same number of electrons in each equation. So we've got 5 electrons in the top equation, which means we need 5 in the second equation. So I need to times this whole equation by 5 to ensure that I have 5 electrons. Once I have done that, I can add the 2 together. So I'll just times it by 5 here. So I'll then end up with 5 Fe2+ ions, 5 Fe3+ ions, and 5 electrons. And then I can add these 2 equations up. So I add everything on the left hand side of both equations and then everything on the right hand side. So I've got 5E- from here plus MnO4- plus 8H+ plus 5 Fe2+ reacts to give me, and then everything on the right hand side is my Mn2+ plus my 4 waters plus 5 Fe3+ plus 5 electrons. We want to simplify this down, and I can do that by cancelling anything that appears on both sides of the equation. So I've got 5 electrons on the left and 5 electrons on the right. And so my overall equation is therefore, and I'll write this in our answer, is MnO4- plus 8H+ plus 5 Fe2+ reacts to give me manganese ions plus 4 waters plus 5 Fe3 plus. And that's your balanced ionic equation for the reaction. Next question asks about the colour observed at the end point of this titration. So it's not looking for the colour change, it's looking just for the end point. And if you remember when we were doing these titrations, we were looking for the first persisting pink colour. So the colour observed at the end point is pink. Part 3 asks for the formula of the ion responsible for the colour observed at the end point. Okay, and yes, our iron. So let's have a think about what this could be. Our iron is being oxidized, iron 2 plus is being oxidized up to iron 3 plus. Have a think about your colour of solutions of iron 2 plus and iron 3 plus. Iron 2 plus is a pale green solution, iron 3 plus is a yellow solution. So it's not going to be that. Something else that's responsible for colour would be our manganate or our manganese ions. So here we've got manganate and here we've got manganese. Well, think about what we're adding in this titration. So what is in our burette? Well, we always have our potassium permanganate in the burette, the purple liquid. And we get to the end point when we've added just enough potassium permanganate or just a little more permanganate than we need. And it is the permanganate that is purple. And once we've added it, got to our end point, that permanganate persists in our conical flask solution. And that's why it is responsible for our pink colour. So it's actually our manganate. Even though that appears on the left-hand side of the equation, it's because it's the point where we've just added enough of our permanganate. The next part of the question is on minimising error, but you'll notice that it is specific to overshooting in titrations. So your question or your answer cannot be just how we minimise error in general, but must be in relation to how we minimise error in relation to overshooting a titration. What your first thought should be with this is not to panic, is not to think, oh, I didn't learn this off, but it's just to put yourself in the lab, pretend you're doing this paper as previously would have been done in the lab, and think to yourself, what would I do? What do I do when I'm carrying out a titration in order to prevent myself from overshooting, from getting too large a value? And the first thing we always do with this is to perform a rough titration. So that could get you 1 mark. And the reason that we perform a rough titration is that it gives us the general idea of where the end point is going to be. It's not a precise end point, but it gives us the area where it's going to be, so that then we can start adding a bit more slowly, approaching that point, and get a more accurate titer. So once we've got our rough titration, so that would be worth 1 mark. The next time we do it, the first accurate, we can add dropwise. Add our solution dropwise before the end point. Okay, and that's another mark. Another thing that we do practically in the lab is that we repeat our accurate titrations until we get 2 values that are within 0.1 of each other. So either 0.1 greater or 0.1 less, and that gives us a good accurate reading. So that's the third mark you could have said would be repeat until values within plus or minus 0.1 centimeters cubed are obtained. So they were looking for any 2 out of those 3 points. Now there are other points that we do practically in the lab that would be worth mentioning, but haven't necessarily been mentioned by the mark schemes, and these are the 3 that they would tend to look for. So I would ensure that these, at least 2 out of 3 of these are mentioned, and then if you want to go on and say something else, you can do, and that would be things like rinsing around your conical flask to with deionized water towards the end point to ensure that all your solution that has been added from the burette has actually made it into your solution in the conical flask. So things like that you could also say, and efficient swirling obviously as well to make sure that our solution is thoroughly mixed. But those are the 3 points mentioned there are the key ones that they would be looking for. Now, the next part of the question is another explanation of practical techniques, and that is how we get our crushed tablets and how we make them up to a 250ml solution. Now, again, this is specific to the question that we have in front of us. But when you're asked how to make up a standard solution, it's always the same key points. Now, here we've been told the mass of our iron tablets. So it is good to, although we've got general points here, it's good to mention the specifics because we've been given actual values. So the first thing we need to do is we need to weigh out our 6 grams of iron tablets. Weigh out 6 grams of iron tablets on a balance. Now, the mark scheme, you didn't have to say the mass, so they put that in brackets. But because you have been given it in the question, it is good to be specific. The second point in general is that we want to then dissolve it in the minimum amount of water. Okay, so we want to dissolve our tablets in the minimum amount of water. So in general, we want to dissolve in the minimum amount of deionized water. Okay, that would be our general point, but for this, for the mark scheme, what they're looking for is how they phrased it is in a beaker. Add, and then again they have a value in brackets, and that's 50 centimeters cubed. So that's quite a small amount, obviously less than the 250 centimeters cubed. So add roughly 50 centimeters cubed of deionized water to the tablets, and then we want to stir to dissolve. Now, you wouldn't get 2 separate marks for this, but you would get 1 mark for a combination of these. Once we have done that, we need to transfer our solution into our volumetric flask. So we need to transfer into the volumetric flask. But there's something important that we need to do, and that is we don't just add it in from the beaker. We must rinse around the beaker and add the rinsings into our volumetric flask as well. So how they phrase it is transfer with washings. Into, and again we've been told specifically the volume that we want to make it up to. So it's a 250 centimeters cubed volumetric flask that we need. After it's in our volumetric flask, what do we need to do? Well, think again, how would I do this practically? And that would be make up to the mark with deionized water. And finally, we want to stopper and invert it. So although we have 5 or 6 key points here, it is only out of 4. You have a maximum of 4 marks. But this is the full process of what you would do. And again, don't panic with this sort of question. This is something you've done time and time again. So basically, your first part is to weigh out your solid. Second step is dissolve it in the minimum amount of deionized water. So the minimum volume of water. Okay, so that gives us a solution of our tablets. What we want to then do is transfer that into a volumetric flask. But when we add it, there's still going to be some residue around the sides of the beakers, and so that's why we rinse around the beakers and transfer the washings into the volumetric flask as well. So that'll give us about that much in our volumetric flask, and then we need to make up to the 250 mark, and then we put on a stopper and we invert it. Okay, so that's how you make up a solution. And again, don't be thrown off by these specific questions because the general method is always the same. Weigh out your solid, dissolve it in the minimum amount of water, transfer it into volumetric flasks with washings, and make sure you include that with washings. So that means just rinsing around the beaker that you use to dissolve your solid in. Transfer with washings into the volumetric flask, make up to the mark using deionized water, and finally stopper and invert. And once you've learnt that general method, you can apply it to any solution that is asked of you to make up. So any solution you're asked to make up, it's always the same general steps. So the next part of the question is our titration calculation. And you can see that we've been asked to calculate the percentage of hydrated iron sulfate in our tablets. Okay, and as with any titration calculations, you must always start with your equation. Even if it doesn't ask you to write your equation at this specific point, it's imperative that you write it in. At AS, your calculations would have been split up and you would have been asked to write the equation at the relative point. But with this, at A level, with it being less structured, you need to go ahead and write out your equation. Even though you've written it on the previous page, write it in again here where you can clearly see it. So we've got manganate, acidified potassium permanganate, that's where the H plus comes from, plus our iron 2 plus ions, which comes from our iron sulfate, reacts to give us manganese ions plus water plus our iron 3 plus. And just as I've highlighted by forgetting, it's important that you remember to balance your equation. So remember, we needed 5 Fe2 plus ions to give us our 5 electrons. Okay, the next place that you need to start is almost always with your average titer. Your average titer. So what we do is we write what we know underneath the relative part of the equation. So don't just jump ahead. Say that your average titer is 22.4. Yes, great. But we need to say, we need to see what that is of. So in our burette we had potassium permanganate solution and its concentration was 0.02. So the first thing I do is write down what I know underneath the relevant part of the equation. So I know that my permanganate concentration is 0.02 molar. And I know that the average titer of this was 22.4 centimetres cubed. That means I needed to add 22.4 centimetres cubed of my manganate to get to my end point, to get to my first persisting pink colour. Then I need to choose my relevant moles equation. And I've got a concentration and I've got a volume, and so I'm going to use the equation N equals CV. My concentration is 0.02. And my volume is 22.4 divided by 1,000 because we're working in centimetres cubed here and we need it into decimeters cubed. Putting that into our calculator, we get 0.000448 moles. So I added 0.000448 moles of permanganate. So let's see how many moles of iron that corresponds to. So drawing our arrow up to the iron part of the equation now, I need to look at my balancing numbers. And I can see that my ratio is 1 to 5. And so that means for every 0.00448 moles of permanganate, I have 5 times as many iron ions. And so we need to do 0.000448 moles times by 5, which gives me 0.00224 moles. Now, I need to think about what I have here and the volume of solution that this is in. So, you can see that the question has told me that I have been titrating 25 centimetres cubed of the iron tablet solution. So this value that I've got here, my number of moles, that is the number of moles in 25 centimetres cubed. But what did I take that from? Well, we need to go back to the previous page where we're told that we made up a solution to 250 centimetres cubed. So what I've got here is I've got 25 centimetres cubed sample out of 250. So basically what I've got is 1/10 of my total volume of solution. So if there's 0.00224 moles in 25 centimetres cubed, that means in my total volume of solution, I've got 0.0224 moles in 250 centimetres cubed. Okay, the reason I need to scale that up is because I need to compare it with the mass of iron that I added in the first place, which was all transferred into the volumetric flask. Okay, so from this number of moles, I can work out the mass. I can work out the mass of iron sulfate that I've produced. Okay, so first of all, I need to work out my RFM because I'm going to be using the equation mass equals N times RFM. The RFM of FeSO4 dot 6H2O is equal to 56 from your iron plus 32 from your sulfur plus 4 times 16 for the oxygens plus 6 times 18 for the water. So 18 is the relative formula mass of water, and you can see that I've got 6. Add that all up, you should get 260 as our RFM. So that means that the mass is equal to 0.0224 times by 260, which gives us a mass, the mass of our iron sulfate, hydrated iron sulfate in our tablets is 5.824 grams. That's the mass of, in 6 grams of my iron tablets, that there is of iron sulfate. And so lastly then I need to work on calculating my percentage. So it has to be calculated as a percentage. So what I know is that 5.824 grams out of 6 grams is iron sulfate. And so to work out my percentage, it's going to equal the mass of my hydrated iron sulfate as calculated previously. Mass of iron sulfate crystals divided by the mass of the iron tablets that we added in the first place. Times by 100%. So that's going to equal 5.824 grams over 6 grams times by 100%, which gives us 97.1%. So that means that 97.1% of my iron tablets is actually iron sulfate with 6 waters of crystallization. So there's quite a lot of iron that makes up those tablets. The next part of the question is a form of identification test that relates to this specific example of the titration. And what it's asking about is the use of potassium thiocyanate to test for iron 3 salts. So it gives us a bit of background information about why it's asking this question. And we know that in this reaction, from our main equation, that iron 2 plus ions are oxidized up to iron 3 plus ions by our oxidizing agent, which is our potassium permanganate. And what you would have learnt last year, and it's one of your identification tests from this year, although it's not all that commonly used, is that potassium thiocyanate can be used to test for iron 3 ions. And it's a very sensitive test. You only need to add a very small amount of potassium thiocyanate to see this happening. And what you produce, your characteristic result of this test, which you should know, is that you form a blood red solution. So what they're looking for here is, in particular, blood red, but you probably also want to say that you form a blood red solution. So that's a positive test for iron 3 ions using potassium thiocyanate. And the reason that is because, so what we have up to then is our hexa-aqua iron 3 complex. And what we're doing is the formula of potassium thiocyanate is KSCN. So what we're doing is we are adding in a thiocyanate ligand, and that takes the place of one of the waters. And so what we end up with is Fe and then just 5 waters and a thiocyanate ligand. Okay, now we need to think about our overall charge of our complex now. So our overall charge of our complex was 3+, but we've added in a negative ligand. And so yes, the charge of my iron is still 3+, but the overall charge of the complex is now 2+, because I've added that negative ligand in. And we've replaced one of the waters, so we need to write that on the right hand side as well, plus 1 water ligand. And at the end you can check that your charge is balanced. So on the left hand side we have 3 plus and minus, so that's overall a charge of 2 plus. And then on the right hand side we have a charge of 2 plus, and so our charge is balanced. So that's important to check when you're writing equations for ligand replacements, that you make sure that the charge given outside your brackets of your complex is not the charge of the metal, transition metal, it's the overall charge of your complex, and make sure that those balance on both sides of the equation. The next section is your deduction section. And so what they will do is they will give you a set of observations and they will ask you to make deductions from that. Previously in the lab you did your observations and then made deductions based on what you saw. This time they are giving you a set of results and asking you to deduce results from that. So although the first box is shaded, what that means is that you don't need to do you don't need to write any deductions in this box here. But it's important that you don't just skip by that, that you read what the observations are, and that should get you thinking about what this solution or this compound might be, because at the end of it you'll more than likely be asked to give the formula of it or identify what it was. So what we can see is that when we dissolve it, we've produced an orange solution, and you should be familiar with all of these tests, and you should be familiar with the colours of your transition metal ion solutions. So when I see orange, even though I don't have to write it in my deductions, the two possibilities for that is that I have dichromate ions present, or the other possibility is that I have iron 3 plus ions present, and that would give me a yellow or orange solution. So at the back of my mind I'm already thinking this could either be dichromate or it could be iron 3 plus ions. But then the next test confirms it. I'm adding concentrated ammonia, or it could actually just be dilute ammonia. And that, again, as we practice with our observations, it would be helpful to write on the left hand side what this is testing for. So ammonia is testing for the metal cation. And it can be dilute or it can be concentrated. And what we produce is a rust precipitate. A rust is kind of like a brown colour. And what this tells us is that it confirms that we have iron 3 plus ions present. So that's what they're looking for. They're looking for you to say that it confirms that there's iron 3 plus ions present. And the reason that we're saying is confirms is because we already got an inclination from the colour of our solution that it might be iron 3 plus, but this test confirms it. You can also say for this answer, not just that it confirms iron 3 plus, you can also say that the precipitate that you form is actually of iron 3 hydroxide and that's just another way of writing the same deduction. So either confirms that there's iron 3 plus ions present, which is probably the easier one to go for, because the second one requires you to remember what the precipitate you've formed actually is. Okay. Test number 3 is with barium chloride, and you should already be thinking that barium chloride tests for sulfate ions. And that's because if there's sulfate ions present, what I'll form is barium sulfate. And as we've discussed before, barium sulfate is totally insoluble. That's why it's used in medical testing, because we don't want it to dissolve into the blood. Barium sulfate is really insoluble, so when it picks up a sulfate ion, it's then insoluble in the solution, and so it appears as a white solid because it's a group 2 ionic compound. So that means it's white and it's insoluble, so that's why we see it as precipitate formed. We can see here that we have a white precipitate. Now they may give you a negative test, they might say no change, in which case your deduction would be no sulfate ions present. But in this case we do see the white precipitate. So our deduction is that we have sulfate ions present, or just sulfate present is also fine. So that would be of your 1 mark. Okay, so although that is quite short, we already have enough information to deduce what we need. So what we can tell is that our salt contains iron 3+, and it contains sulfate, and so it must be iron 3 sulfate. So the second part asks us to give the formula of salt A. So I know that I have iron 3 sulfate. So I need to write my formula for that. And what we need to do is we need to split that up into the 2 different parts. So we've got iron and then we've got sulfate. We get the valency of iron from the oxidation number. So oxidation number is 3, and so my valency of iron is 3. Sulfate has a charge of 2-, and so that means its valency is 2. When we swap and drop those, the 2 now belongs to my Fe, and the 3 belongs to the sulfate, but I need to put that in brackets to show that the 3 applies to the whole sulfate part. So my formula is Fe2 brackets SO4 3. And make sure you do your working out for that to ensure that you have the correct formula.